to this class of Engineering Mathematics 3, DEG1301, from the School of Engineering, Energy and the Built Environment in the Department of Electrical and Electronic Engineering. My name is Jackson Gatuire. Today we are going to learn about vectors. And other vectors, you, a student, you are supposed to, by the end of this topic, you are supposed to know the following or be able to do the following. One, to differentiate between a scalar and a vector quantity. Also, you should be able to solve the gradient of a vector. Also, you should be able to explain the meaning of dot and cross products. Also, you should be able to compute dot and cross products given either algebraic or geometric information. Also, you should be able to apply dot and cross products in many areas, like in solving angles, in getting the orientation of axes, scalars, and vector projection. An introduction of the vector analysis. The vector analysis, as a definition, is a branch of mathematics that deals with the quantities that have both magnitude and direction. Some physical quantities are entirely defined by numerical values and are called scalar quantities, or they are called simply scalars. Other quantities are defined by numerical value and direction in space, and these are called vector quantities or simply vectors. Now, we have got examples of each of these, and other scalars, we have got mass, we have got temperature, we have got volume, we have got speed. Other vectors, we have got force, we have got moment, we have displacement, we have velocity. Remember, I have said that the scalars are only those which are defined by just the magnitude, and that is the scalars. And the vectors are those which are defined by the magnitude and direction. If I give an example on the velocity and on the speed and the velocity, and if I say that I am moving at 40 kilometers per hour, now, that information may not be so much helpful to someone who perhaps want to know where exactly I am. And that way, that is a scalar quantity. But if I say that I am moving at 40 kilometers per hour east, then there is an aspect of magnitude and an aspect of direction. And that is a vector quantity. And therefore, if someone wants to get where I am, then after about a given amount of time, then someone will be able to get me. And if, for instance, there are two persons who are moving in different directions at the same speed, then you would know that if one is moving at, for instance, moving at 40 kilometers per hour in this direction, and the other one is moving at 40 kilometers per hour in this opposite direction, then automatically you are going to know that after 1 hour, they are going to be 80 kilometers apart. So that is vectors. And you can see there is a big difference, because now these other scalar quantities, they cannot be expressed in terms of direction. Like mass, you just mentioned of kilogram. Temperature, it is just degrees Celsius or Kelvin. So that is the difference between the scalars and vector quantities. Now, we have got ways through which we are able to distinguish vectors from scalar quantities. The first way that we usually use is bold print. So in printed work, you are going to get that the vectors are usually bold, indicated by bold letters. And then you may also use two capital letters with an arrow above them. So such that the arrow indicates or shows the direction of the vector. such that if it is AB with an arrow above it, then you know that A is the starting point and B is the end point, and the direction is shown by that arrow. Also, you may also have got a line, just be a line above the alphabets or the letters, or just if it is just one letter, you have got a bar on top of it, and still that is a way of showing that that is a vector quantity. You may also have got an arrow on top of the alphabets, maybe uppercase or lowercase letters. Still, this one is a way of showing that that is a vector quantity. Also, you may have, if for instance you have a vector which is drawn on a Cartesian plane, then you may use the vector units or unit vectors which have got a magnitude of 1, such that you have got the x coordinates, you have got the y coordinates, and this is another way of indicating or showing a vector quantity, where I and j are the axes at right angles to each other. And an example of such kind of a vector is, for instance, you have got 3i plus 4j, which this means that there are 3 units in the I direction, and you have got 4 units in the j direction. And we have got a diagram here which depicts exactly what I've said. And this line is a vector which has got the first coordinate is this, or the starting point is 0, and we have got the end point is indicated by 3, 4. Note that there is a difference in the way we usually express the a point and a vector. And a point is usually shown by use of parentheses, or what we simply say they are brackets. And the vectors are usually denoted by symbols of or signs of inequalities. So if you have got this kind of an illustration, then means this is a point and this is a vector. Now, to get the magnitude of a vector, which has been given like 3, 4, or it has been indicated by the coordinates 3i plus 4j, then we usually use the formula which you have got. If the vector is OA, you get the magnitude of that vector, which is shown by these 2 bars, or what you also called the modulus. So this is given by the components of the x or the I coordinate squared plus the components of the j coordinates squared, and then you get the square root. An example for that, for instance, we have got a vector which has got an initial point which is 1, 2, and the terminal point is 5, 1. And then you are told to determine the component form of the vector. Now, to get the component form of that vector, now we have the starting point. So the start point is 1, negative 2, 1, comma, negative 2. You must put a comma to show that it is a point. And then the end point is shown by 5 and 1. It's shown by 5 and 1, or 5, comma, 1. And then what we want to get is the components of the vector. The way I have said that you show using the inequalities or signs of inequalities. So this one, you subtract the x or the I coordinates, and then you put a comma, and then you subtract or get the difference of the j coordinates, such that the x or the I coordinates we know for the start is 1, and for the end is 5. The j coordinates is 2 for the start, negative 2 for the start, and 1 for the end point. Therefore, the coordinates are going to be, or the components are going to be 5 minus 1. That is the first part, then comma, and then we have got 1, which is at the end point, minus 2. And then this, we show that this is a component of a vector, and therefore what you get here is 4, and then a comma, and then this one is going to be 3. So this is the coordinate of component of that vector. And you can also be told to get the magnitude of that vector. The magnitude of that vector we get, or we use the formula which we have seen that previously, where we have said that the magnitude of vector OA is given by the x, the components of the I coordinate squared plus the components of the j squared, and then you get the square root. And from this point, we have got the x is shown by 4, and the y is shown by 3, and then you square that, and then you get the square root, and of course, you are going to get the answer as 5. So that is the way you get the magnitude of a vector. The magnitude of a vector. Or simply, you get the change in the x-axis over the change in the y-axis squared, because this is simply the change in the x-axis, this is the change in the y-axis, and then you square them, and then you find the square root, and that will be the answer for that question. Now, the last way of showing or expressing vectors is by use of unit vectors, in which we have got the 3 dimension, whereby we have got the I, we have got the j, and we have got the z, of which the I represents the x-axis, the j is the coordinates on the y-axis, and k is the coordinates of z-axis. Remember, unit vector have got a magnitude of 1. And therefore, if you want to show the coordinates or the components of I, it is shown by 1, 0, 0, whereby 1 shows the magnitude of the I component. And the j component is going to be shown by 0, 1, 0, and of course k is shown like that. Such that if you have got a vector which is given by 5, -2, 9, then simply you put these unit vectors, and then you are going to have 5i minus 2j plus 9k. So this is a representation of a vector which is given in 3 dimensions. Then we have got something which we call algebra with vectors. Remember, algebra and vectors, they have got some kind of relation, or the vectors, they borrow a lot from the algebra, and this is useful when we are doing some calculations in vectors. And for instance, if you have got a vector which is given by 5i minus 2j plus 9k, and then it is multiplied by a scalar 3, then this is going to be distributive, or we have got a rule which says that you distribute this 3 in the components of every term which is in the bracket of that vector, and therefore it's going to be 15 minus 6j plus 27k. Now, an example we have, if for instance you have got a is given by 2i plus minus j plus 4k, and b is given by I plus 6j minus 2k, and then you are told to determine part 1, you get 2a plus 3b. So what this means is that you multiply the first component of the first vector with 2, or with scalar 2, and then we have got the second vector b, you multiplied with a scalar 3, and then you get the sum of the 2. So what are we going to have? So we have got 2i so we have got 2i minus minus j, 2I minus j plus 4k. This is our A, and our B is given by I plus 6j, I plus 6j minus 2k, minus 2k. And then you're supposed to get 2a plus 3b. So in this one, you've said that you multiply 2 by the vector which is given, and therefore you are going to have, when you multiply here, you are going to have 4I minus 2j plus 8k. This is going to be the value of 2a, and then you have got 3b, which is going to give us 3I plus 18j minus 6k. So that is 2a plus 3b. And then you put the like terms together. Where you have got i's, you put them together, j, you put them together, so that you get the vector. And then, therefore, this is going to be 4i plus 3i is going to be 7i minus 2j plus 18j is going to give us plus 16j, and then 8k minus 6k is going to be plus 2k. So this is our vector, or this is the result of having 2a plus 3b when you have used the algebra in the vectors. And then you have got the second part, which is asking you to get 5a minus 4b. Therefore, again, you multiply the whole of part A with 5, the whole of part B with 4, and then you subtract. And what you are going to get is that the whole of this one multiplied by 5 is going to be 10i minus 5j plus 20k. And then this one you are subtracting, the whole of this one multiplied by 4 is going to be 4i plus 24j minus 8k. Again, you put the like terms together. Remember, this negative here is going to affect the signs which are inside here, and therefore, like this sign is going to be negative, this sign is going to become positive, and therefore, you are going to have 10i minus 4i is going to give us 6i, and then minus 5j minus 24j is going to be minus 29j, and then plus 20k plus 8. This we have said is going to change to positive, is going to be plus 28k. And then this is our answer for that question. That is the answer for that question. Then we have got vector addition. Vector addition is when you have got two vectors that you need to add them together, and then you get the result, of which the result is like the magnitude or the length of that vector, and then you also need to know the direction of that. So vectors, as we had said earlier, they are usually represented by a line, the length of the line being proportional to the magnitude of the vector, and the direction of the vector is shown by the arrow. The arrow denotes the sense of the direction of the vector. And then there are two ways through which you can be able to solve vector addition. One way is what we call head to tail or tip to tail method, and also we have got the second one which we call the parallelogram method. Now, we have got the first one, which is shown by this diagram here. So our vectors are V1 and V2. V1 at an angle of beta 1, V2 at an angle of beta 2 with the horizontal. And then we have said that you have two methods of doing the vector addition. The first one is head to tail. That is, this is the head of the vector, or the tip of the vector, this is its tail. So you join the head of the first one with the tail of the second one, such that you are going to have this vector V1 is represented by OA, make sure that you draw it. If, for instance, you want to get the answer through construction, it should have the same magnitude and exact angle. Same magnitude and at the exact angle. And the same case with V2, which is represented by OR, and it should have the same magnitude and at the same angle with the vector V2. And then the resultant is going to be from where the first one was starting to where the last one is ending. So this is the resultant of the vector addition of V1 plus V2. So that is the head to tail method. And then using the parallelogram method, this is shown by the second diagram here, we have got the vector V1 and the vector V2. You complete this as to form a parallelogram. So this side is similar to this side is similar to this side. So this one you will draw it here, and this one you will draw it here, and therefore what is going to be formed is a parallelogram. Now the diagonal, the longer diagonal of that parallelogram is going to be the summation, or the sum of V1 plus V2. Okay? Now, you may have more than two vectors which are being added together. That should not be a problem. And what you just do is to make sure that the vectors are drawn with the same magnitude and with the same angle. For instance, you have got here, we have got V1, V2, and V3. And then to get the resultant of this, you have got V1 redrawn there with the same magnitude at the same angle. V2 is drawn there. Of course, here we are using the head to tail method, and then we have got V3. And I said the resultant is going to be where the first is starting, or where the first vector is starting, to where the last one is ending. So this is going to be our resultant vector. The order actually is not something that should matter. You can start with any, you can start with V3, you can start with V2, as long as they have got the same length and they have got the same direction. Now, here we have got an example. We have got a force of 4 newtons is inclined at an angle of 45 degrees to a second force of 7 newtons. Both forces acting at a point. Find the magnitude of the resultant of these two vectors and the direction of the resultant with respect to the 7 Newton force. So this has been drawn here for us. We have got our 4 Newton vector and our 7 Newton vector. The angle between them is 45 degrees. The angle between them is 45 degrees. Then we want to use vectors to be able to get the resultant of these two vectors and the direction of that vector. Remember, if you just get the magnitude and you not give the direction, then that one cannot count as a vector. So this one, we are going to redraw this vector such that 7 is going to remain the way it is. We have got this is a 7 Newton, and then we redraw this 4 Newton from where the 7 is ending, and then at the same angle with the same magnitude, and then the angle between them is 45 degrees. And of course, now the resultant is going to be given by that vector, which is our R. So that, let's say that is our resultant R. And then we are supposed to get the magnitude of this vector, and this is 4 newtons, and we get the direction of that vector with the 7 newtons. So this, let that one be our angle alpha. So here, for us to be able to solve this, we are going to borrow some knowledge on the cosine rule, whereby if you have got a current triangle which has got side A, side B, and side C, and the angles are such that this is A, this is C, and this is B. And then here, we want to get the value of side A. So remember here, we usually get A squared is usually given by B squared plus C squared, then minus 2BC cos A. So if we borrow this, we can be able to solve our value of R here, or the resultant vector here. So this angle, remember, it's the angle which is opposite that side which you are looking for. So that's why we have indicated with capital letter here. And then if we refer this one, if we, for instance, assume or let 7 Newton to be equal to A and 4 Newton to be equal to B vector, and this is our resultant R vector, then we are going to say, then we are going to have that our R squared is going to be given by A squared plus B squared minus 2AB cos of the angle that is opposite this, which is this angle, and it is given by, if you subtract 180, you are going to get this is 135 degrees. So this is cos 135 degrees. And then you come and replace this with the values. This is 7 squared plus 4 squared minus 2 times 7 times 4, and this is cos 135 degrees. Now, this, of course, is going to give us 49 plus 16 plus this is 28, this is minus, sorry, this is minus 56 cos of 135. So 135 degrees. So when you work this one out, you are going to get our R squared is going to be a value which had worked this one out. This is 104, 104 point. This is going to be 104.6. And then you get, of course, the square root of that. And then our R is going to be around 10.22 newtons. Remember, it is force, and therefore it's going to be in terms of newtons. So 10.22 newtons is the value of this vector, which is the resultant of having the 7 newtons and the 4 newtons at an angle of 45 degrees. Then we need to get the direction of this vector. So the direction, again, if we come back to this, formula here, if you want to get the value of this angle, cos A, of course, you make it the subject of a formula. You are going to have this is going to be equal to B squared plus C squared minus A squared all over 2BC. So that way, you can be able now to get the cos inverse of A, and then you get the angle A. The same case, if we come here, we can be able to get the value of this angle here. Remember now, this one is opposite B. This is opposite B, and therefore, if you want to get the cos of our angle alpha, is going to be, this is going to be given by, now, it is between these two, like what we had that A is between B and C, so that is what we have here. So this is between R, so this is going to be, we are going to have R squared plus A squared, R squared plus A squared minus the side which is opposite, the side which is just opposite the angle, and our side which is opposite is 4, so this is minus 4 squared all over 2RA, or 2AR, okay? Then we put the values, of course, this is going to be given by, our R now is 10.22, just use 10.2 squared plus 7 squared minus 4 squared, which is 16, and then all over 2 times 10.2 times 7. So you get cos of A is going to be equal to that. Cos of A is going to be equal to that. And then you get that when you calculate that, you are going to get that cos of alpha is going to be given by around 0.96. And then you get the cos inverse. So cos inverse of 0.96 is going to give you around 16 degrees. It's going to give you 16 degrees. So this is, so, and then you come and write the vector or the resultant. So the resultant is going to be 10.2 newtons at 16 degrees. So that is how now it becomes a vector. So the magnitude and the direction. So 10.2 at 16 degrees with, of course, it was with the 7 Newton. It is 16 degrees with the 7 newtons. So that's the way you handle that kind of a problem. Now, there is something that we call resultants or resolution of vectors. Now, resolution of vectors is like now moving in the reverse of what we have got when you have got two vectors and you get the resultant. So here you have got one vector, or you have got, we have got one vector, which is like, for instance, given f, and then you are supposed to resolve this into vertical and horizontal component. So what you usually do is that, remember, this is going to form, like if you take this side and bring it here, it is going to form a right-angled triangle. And therefore, to get the, from the cosine rule again, trigonometry, you are going to get that the sine of this angle is going to be given by opposite of hypotenuse. And this opposite is the same as this. So to get this side is going to be f, which is the hypotenuse, sine of the angle. And to get this side, you use cos. So cos of this angle is going to be given by adjacent over hypotenuse. And therefore, to get this side is going to be given by f cos theta. So that way is resolving this vector f into having vertical and horizontal components. So remember, if again you have been given the vertical and horizontal component, you can be able to get this resultant, which is like what we have just previously done. Now, we have got an example here. Resolve the acceleration vector of 17 meters per second squared at an angle of 120 degrees to the horizontal into a horizontal and a vertical component. Now here we have got, we need to draw this so that we are able to understand it well, and therefore we have got a Cartesian plane, and we have been told that this force or this acceleration is of 17 meters per second squared at an angle of 120 degrees. So if you get an angle of 20 degrees is from somewhere there to somewhere past 90, so somewhere, because we usually take the angles from the horizontal going in the anti-clockwise, and then this is going to be somewhere there. So this is our acceleration, which is 17 meters per second squared. And then you are supposed to get the result, you are going to resolve that into horizontal and vertical components, and therefore the vertical component is going to be this, and the horizontal component is going to be this. So using the formula which we have seen in the previous diagram, to get the horizontal component abbreviated with h is going to be given by h is going to be given by 17 meters per second squared, 17 meters per second squared cos. This is 120 degrees cos 120 degrees. Okay. So if you get 17 meters per second squared cos 17 is going to give you negative 8.5 meters per second squared. So this is negative because it is going in this direction, or this just tells you that this vector is moving in the opposite direction other than going in the forward direction. So this is why we have got this negative here. After all, if this is a Cartesian plane, these are x coordinates on the negative side. So that is the horizontal component. And then the vertical component, abbreviated with V, is going to be given by V is equals to 17 meters per second squared, sine of 120 degrees. Sine of 120 degrees is going to give you a positive, and then a positive value, and then you multiply here, and the answer which you are going to get is 14.72. 14.72 meters per second squared. Okay, 14.72 meters per second squared. So this is the resolution of that acceleration into horizontal and vertical. So this is our vertical component here, V, and this is our horizontal component, H there. And then here you have got an exercise which you need to attempt on this or under this resolution and vectors. And the question is asking, calculate the resultant force of the two forces given in example 2. Remember, example 2 is the one which was having the 4 newtons and the 7 newtons at an angle of 45 degrees. Then you're supposed to get the resolution of that into horizontal and vertical component. Remember, just to give you a hint, is that when you have got two vectors, what you need to get is just the summation of the two. You get the cosine of the first vector plus the cosine of the second vector, and that will give you the horizontal component. And the vertical component will be the sine of the first vector plus the sine of the second vector, and that will give you, of course, multiplied by the initial vectors, and then multiplied by, you add them together, and then that will give you the vertical component. Now, there is what we call vector subtraction. At a vector subtraction, if you have got a vector f, which is represented by OA, and then you have the vector given as a negative OA, it just simply means that it is that vector f going in the opposite direction, such that if this is our vector OA, the initial vector, which is represented by f, and then you are given negative OA, or you are given negative OA, then it simply means that it is the same vector, the same magnitude, but now what changes is the direction. So it moves in the opposite direction. So OB is equals to negative OA. So OB is equals to negative OA. So the negative here means the change of direction. The negative means the change of direction. Now, if you have got two vectors which you need to do the subtraction, now two vectors acting at a point shown by, for instance, this diagram here, or this vector diagram here, we have got vector OA and vector OB, and then you are supposed to get the difference between the two vectors, or simply you get OA minus OB. Okay, so you want to get OA minus OB. Remember, in vector subtraction, it is like having OA, or else you have got OB plus what you are now subtracting, which is a negative vector. So here we have got OB, we are subtracting OA. So we are going to have OB is going to remain the way it is, but OA is going to change the direction, as we have said. So the diagram which you are going to have is the second one, such that we have got OB remains the way it was drawn initially, but now OA is drawn in the opposite direction. Okay, and then the resultant, because now here you be doing now like the addition of what you have done in the previous one, using now this is the parallelogram method, we are going to have, this is just like having OB plus negative OA, or OA which has been reversed. And therefore, we are going to have the resultant to be equal to OD. This is going to be the resultant of OB minus OA. Now, remember, if you have got this first vector diagram, you can still use it to do both subtraction and addition of the vectors, such that in terms of addition, OB plus OA is going to be vector O, is going to be vector OB. And then the subtraction is going to be the shorter vector. So if this was a parallelogram, then the longer vector is as a result of addition, and the shorter vector is going to be the result of subtraction. Now, we have got an example here. An example is saying that an acceleration of A1, which is 1.5 meters per second squared at 90 degrees, and A2 is 2.6 meters per second squared at 145 degrees act at a point, and then you are expected to find A1 plus A2 and A1 minus A2, and then you draw the vector diagram. So ideally, for me, I would prefer to draw the vector diagram first, and then we find the vectors, the resultant vectors, because this one is going to help us to know which vectors we are talking about. So if again I draw this Cartesian plane like that, we have been told that the first vector, this is the first vector, it is 1.5, it is given by 1.5 meters per second squared, 1.5 meters per second squared at 90 degrees. Then we have got the second vector, which is 2.6 meters per second squared at an angle of, is given at an angle of 145 degrees. So 145 degrees is going to be, so from here you get 145 degrees is going to be around the center of these two lines, is going to be somewhere there. Then get this is 1.5, so 2.6 is going to be somewhere along this, it's going to be around that. So this is our 2.6 meters per second squared. So you are supposed to get the result of, A1 plus A2. So this is A1 and this is A2. So A1 plus A2. So simply this is vector addition. And here, as you can see, we have got these two vectors, and we have said if you want to use the parallelogram method, then you just reproduce this one such that it's going to form a parallelogram like that. This side should be equivalent to this side, and this side should be equivalent to this side, and therefore get the longer diagonal there, which will be our resultant. So this is our resultant of the vector addition, which is going to be A1 plus A2. So that is our resultant vector addition, A1 plus A2. And then how do you now get the value of that? How do you get the value of that vector, that resultant vector? So here you are going to resolve just like what we have done in the resolution of vectors in the horizontal and vertical. This is what you are going to do here. So we are going to have got the horizontal component. We are going to have got the horizontal component, which is going to be represented by H, and H is going to be given by the first vector cosine the angle plus the second vector cosine its angle. So the first vector is 1.5 cos 90 degrees then plus the second vector is 2.6 cos 145 degrees. So this is going to give you 0 because cos of 90 is 0, and then this 2 cos 145 times 2.6 is going to give you around the negative, because cosine here in the second quadrant is usually negative, and therefore this is going to give you negative 2.13 meters per second squared, negative 2.3 meters per second squared. Then we have the vertical component. We get the vertical component. The vertical component, again, this we represent it with V, and we are going to have V, again, is going to be given by the product of the cosine of the sine of the sine of the first vector plus the product of the sine of the second vector, such that we are going to have 1.5 sine 90 plus 2.6 sine 145 degrees. So sine 90 is 1 plus times 1.5 is going to be 1.5, and then you get sine of 145 plus 2.0. So this is going to give you around 1.49. Then when you add 1.5, it's going to give you around 2.99 meters per second squared. Then from there, you get now the magnitude. So the magnitude of this, you get the horizontal component squared. It's going to be given by horizontal component squared plus the vertical component squared square root. Then this is going to be, this is negative, horizontal component is negative 2.13 squared plus 2.99 squared square root. Sorry, this is squared. And then when you work out this one, you are going to get the answer that you are going to get there. It's going to be 3.67. Going to be 3.67 meters per second squared. So that is the magnitude of that vector, 3.67 meters per second squared. And then we need to get the direction. So the direction of that vector, is going to be given by the tan inverse of the vertical component over the horizontal component, which is going to be tan inverse of, we have said the vertical is 3.67 over the horizontal was negative 2.13. So that is going to be around, so the angle is going to be negative 54 point, the angle is going to be negative 54.53, 54.53 degrees. But remember, this vector or this resultant is in the second quadrant, and therefore we need to give it a direction that simply shows that it's in the second quadrant. And therefore, to get that angle, you just subtract 180. You subtract this one because this one has measured from the horizontal going the clockwise direction, and therefore the actual angle is going to be 180 minus 54.53 degrees, and this is going to be given by 147, 140 is going to be 125. Sorry, this is going to be 125.47, 125.47. This is 2, so this is 125.47. 125.47 degrees. And therefore, the magnitude or the resultant, so A plus B is going to be A plus B is going to be given by 3.67 at 125.47 degrees. 125.47 degrees. So this was the resultant, and this is the angle. This is the magnitude, and this is the direction. And then the second part is asking us to get the magnitude of A minus B. So remember, A minus B, this is A1 minus, this was A2, A1 and A2. This is A1 minus A2, A1 minus A2. So remember, just like what we have said, in the subtraction of vectors, you can simply have, this is like addition, we have got A1 plus, now the vector A2 moving in the opposite direction, and therefore this is negative A2. So what we are going to have is the first vector, then plus the negative of the other vector. If it is given in degrees, and therefore we are going to get the reverse of that, minus 1/80 of that. So the horizontal component of this is going to be given by, 1.5 cos 90, and then this is plus 2.6 cos, so this is the angle here. Now we have said that it's going to change the direction. So this was 145, and therefore when you change direction, you subtract 180 degrees, and then it's going to change direction to the opposite direction. So you just subtract. So this sign simply replaces this negative A2. And therefore, what you are going to have here is simply this is going to be 0, this is going to be 0, and this is going to be plus 2.6 cos of negative 35 degrees, which is going to give you a value which is 2.13 meters per second squared. 2.13 meters per second squared. And then the vertical component, you just do 1.5 sine 90 plus 2.6 sine. So this one, again, you just do it the same, so it's going to be sine negative 35 degrees. And then the answer which you are going to get there is going to be 0. Because here, you are going to have sine of 90 is 1. This is going to give you 1.5. Sine of 35, you are going to get around 1.499. And therefore, when you approximate that one to be 1.5, then it is negative, so it will be 1.5 minus 1.5, which is going to give you 0. And therefore, our magnitude, so the magnitude of A1 minus A2, the magnitude is shown by that, is going to be given by the square root of the horizontal squared and added to the vertical squared, such that it is 2.13 squared plus 0 squared square root, and of course this one remains 2.13, and this is meters per second squared. Now we have got the magnitude. Now again we need to get the direction of this, and the direction of this one, just like the previous one, is going to be given by the tan inverse. So direction is going to be given by the tan inverse of the vertical over the horizontal, which is going to be given by the vertical is 0. So this is tan inverse of 0 or over 2.13. Of course, this one gives you 0. This is going to give you 0. And this is because if we reproduce, if we go back to the vector diagram which we have drawn here, if we go back to the vector diagram which we have drawn here, and we get the negative A2, this was A1, so negative A2 is going to move in the opposite direction with the same magnitude, so it's going to be somewhere there. So this is going to be A1 minus A2, so this is going to be our negative A2. So that is our negative A2. And then you get the resultant is going to be along this, because if we produce this one to be our parallelogram, then this is going to form something like this, and then this is going to be our resultant vector here, which is going to be A1 minus A2. So you note that the resultant vector is along the horizontal, which is why it has given us an angle of 0. It has given us an angle of 0. So this is the vector diagram that is going to result as a result to have, you are going to have as a result of having A1 plus A2 and A1 minus A2. Then, from there, we have got an exercise. You have got an exercise that you need to attempt, and here you have been given, you calculate the resultant of, you have got V1 minus V2 plus V3, and part 2 you get V1 minus, this is V2 minus V1 minus V3, when V1 is given by 22 units at an angle of 140 degrees, V2 is given by 40 units at an angle of 190 degrees, and V3 is given by 15 units at an angle of 290 degrees. So simply what you do is just like what we have, this we have got 2 vectors here, but now here we have got 3. So simply you get the horizontal components of the 3 vectors and the vertical components of the 3 vectors. And then the resultant is going to be the horizontal squared plus the vertical squared square root. That is going to be the resultant. So when you have got the first case, it's going to be, we have got V1 minus V2 plus V3 and V2 minus V1 minus V3. You just do the same way like what we have done in the previous example. Then we have got vector multiplication. Vector multiplication refers to when you have got a vector and you are multiplying it with a scalar, a number. So what simply happens is that it depends on what kind of a number or value you are multiplying with, such that if it is a value which is more than 1 or larger than 1, then the vector actually increases with that magnitude, such that if you have got a vector u multiplied by 2, what you are going to have is 2u, twice that vector. But in some cases, you can have a vector which is a negative. We mean a vector multiplied by a number which is negative. And it means that it's going to change the direction of that vector. For instance, if this was multiplied by negative 2, then it's going to be the same magnitude, but the direction is going to change. And again, you can have a situation whereby the vector is going to reduce. If, for instance, you have got a fraction which is less than 1, then that magnitude, the magnitude of that vector is again going to reduce. So vector multiplication, it's about multiplying a vector with a scalar. Then there is something we call dot and cross product. Dot and cross product is a part which is very important in the calculations of vectors, in multiplications of vectors. And if we start with the dot product, and this is defined, one of the products of 2 vector quantities is called scalar or dot product of 2 vectors, and is defined as the product of their magnitude multiplied by the cosine of the angle between them. So what simply means, that means is that if you have got 2 vectors which are given by OA and OB, and you get, or you want to get the dot product of that, then what you simply do is multiply the magnitude of those two vectors, and then you multiply with the cosine of the angle which is between them. So the answer that you get on dot product is usually a scalar. The product is a scalar. That's why it is being called a scalar or dot product. So if you perform a vector multiplication and the answer that you get is just a scalar, then that is a dot product. So that is the definition of that. So if you have got two vectors, like V1 and V2, so what we are saying is that if the vector is OA and OB, and their magnitudes are such that the magnitude of OA is V1 and the magnitude of OB is V2, then the dot product, what it means is that you take OA dot OB. This dot is the one which simply shows that you are doing a dot product. So you have got OA dot OB is going to be given by the magnitude of OA times the magnitude of OB, then the cosine of the angle between them. Now, we usually say that dot product follows the commutative law of algebra, which says that if you have got if you have got a vector A multiplied by a vector B, it is simply the same as having, or you are going to get the same answer as having B multiplied by A. And therefore, it does not matter which one you start with. It does not matter which one we start with. Now, let's refer to this example here, and we see what that commutative law means. If you have got this this diagram here, this vector diagram here, which has got OA and has got OB, and you want to get the dot product, then you can get the projection of OB into OA. And the projection of that is that you get a perpendicular. You get a perpendicular from OB going to OA, and then you get this. This is going to be like now the adjacent to this angle. And therefore, the projection of OB into OA is going to be given by V2 cos theta. Okay? Therefore, what you are going to have in the dot product is going to be OA dot OB is going to be V1, which is this magnitude here, times the projection of V2 onto V1 is V2 cos theta. So it is V1 times V2 cos theta. So the same case would happen if now you want to get the projection of OA into OB. Again, you drop a perpendicular from where A is towards B, and therefore the side or the projection of OA into OB is going to be given by V1 cos theta, and therefore to get the dot product, it will be given by V2 into bracket V1 cos theta. So that is the commutative law. The two actually follows the commutative law. The dot product follows the commutative law. Now, if you want to get the angle, the value of the angle which is between those two vectors, vector OA and the vector A, B, and vector, we had two vectors. We had got A and we have got B. Let's represent them by A and B. You want to get the angle between them. Then we have said that the formula of getting the dot product is AB cos theta. So just make this the subject of the formula, and then you are going to have cos theta is going to be given by A dot B over AB. Of course, to get the angle, you get the cos inverse of that, and then you are going to have the answer. Now, let's have an example here. We have got let A be given by A1I plus A2J plus A3k, and B to be given by B1I plus B2j plus B3k. And then you are supposed to get A dot B, that is the dot product. Then to get that, you have got our A is given by A1I plus A2j plus A3k. Remember, these are unit vectors which have got a magnitude of 1. And then we have got B is going to be given by B1I plus B2j plus B3k. And then we want to get A dot B. These are vectors A dot B. And what you do is you take the components of I, multiply it across the whole of B, then plus the component of J, multiply by the whole of vector B, then plus the component of K multiplied by the whole of vector B. So what you are going to have is that for the first part, for the I, you are going to have A1, B1, I dot I. So remember, this one is dot. So that's why I'm using dot, because you are doing dot product. Then I times I. Then you are going to have the second one is A1, B2, I dot J. So it is I now multiplied by J, and then plus A1, B3, I dot K. So it is I now multiplied by this part, and then plus, we come to the second part is A2, B1, J dot I plus A2, B2, J dot J plus A2, B3, J dot K, plus now the last part multiplied across is going to be A3, B1, K dot I plus A3, B2, K dot J plus A3, B3, K dot K. So that is the expansion of that dot product A dot B. And then we need to remember that unit vectors I, J, and K have got a value, or the magnitude is 1, is equals to 1, or the magnitude unit, remember that, yes, have got magnitude 1, let's just let have magnitude of 1. So whatever that we are multiplying here, for instance, I dot I, we can get such that this implies that if you have got I dot I using the dot product formula, this is going to be the magnitude of the first one, which is 1, times the magnitude of the second one, which is again 1, times the cosine of the angle between them, which is 0. They are in the same plane. They are the same axis. I and I are in the same axis. So cos of 0 is 1. And therefore, this is going to give you 1. So any point you have got values which are on the same axis, then the answer is going to be 1. So this is going to be the same as when you have got J dot J, which is the same as K dot K. So that is going to give you a value 1. Okay. On the other hand, if you have got I dot J, for the second case, I dot J, again they have got magnitude 1, 1, so this is going to be 1, and this J is having a magnitude of 1, and then the two of them have got a phase difference of 90 degrees. Remember, this is a three-dimensional plane whereby we said if you have got a three-dimensional plane which is having the I coordinates, the J coordinates, or the K coordinates, all these have got a magnitude of 1. That means that all of them are at right angles with each other. So we have got the I is at right angle with the J, and J it is at right angle with the K, K is at right angle with I, and therefore they make an angle of 90 degrees. So when you are getting the cross product, you get you multiply, or you get the cosine of the angle between them, which is 90, and cos of 90 is 0, and therefore this is going to be 0. And this will happen to any other. This will happen to any other vector which have got an angle of 90 degrees. This will happen to when you have got I dot K, or when you have got K dot J, and so forth and so on. So all those which have got an angle of 90 degrees are going to give you the value of 0, which simply means what you are going to be left with is only those values which have got, or which are on the same axis, I dot I. So you are going to be left with this one, and you are going to be left with this part, you are going to be left with this part. Therefore, our answer to our A dot B is going to be given by A1 B1 plus A2 B2 plus A3 B3. So this is our answer to the dot product of A dot B. Okay, this is our answer of A dot B. And then you have got an exercise here which you need to do, and the exercise is telling you that if you have got P given by 2I plus J minus K, and Q is given by I minus 3J plus 2K, then determine P dot Q. So you just simply do the same way we have done here. And then if you have got the magnitude of P plus Q, the modulus of P plus Q, the whole, you just get the value of P, this is P, add to Q, and then the answer, you get the magnitude of it. And then this is different from this. This is, you get the magnitude of P, then add that to the magnitude of Q. So you are going to get the magnitude of this, get the horizontal and vertical components, and then get the magnitude of that, and then you get the magnitude of this one, and then you add the two magnitudes together. And that is how you are going to handle that. Then we have got the second part of this vector product, which is called cross product, or it's also called vector product. And it is called a vector product or a cross product because the answer which you get as a result of multiplying two vectors is going to be a vector. The answer which you get, the product, is defined in terms of the modulus of the magnitude of the two vectors and the sign of the angle between them. So you get the magnitude of the two vectors. If you have got vector OA and vector OB, then the cross product or the vector product is going to be the modulus or the magnitude of OA times OB is going to be given by magnitude of OA times the magnitude of OB times the sign of the angle between them. Remember, here we usually put n hat to show that the answer which you are going to have here is going to be a vector. Unlike the other one, which was simply a scalar. It didn't have angle. It didn't have the axis I, J, and K. So this is going to have that. Now, this theta, of course, it's the angle between the two vectors, and of course, we usually use this sign. This is the sign that we usually use to show that you are doing a cross product. So this is the cross that we usually use. Now, here, we usually say that if you have got two vectors, we have got vector A and we have got vector B, and then you are doing a cross product or a vector product. The resultant vector, we have said, is going to be, the resultant answer is going to be a product. The resultant product is going to be a vector, and therefore it's going to face a certain direction. Now, this direction that it's going to face is usually shown, or we usually use a screw rule to denote or to get the direction of the vector that is going to be assumed by the resultant vector. Now, what does this screw rule mean or say? Now, we have got a right-handed screw. So a right-handed screw is that which you use the right hand to either tighten the screw or loosen the screw. So the direction in which you turn is very important because it tells you whether the screw is coming out or whether the screw is going in. Now, here we have got the vector cross product. We have got vector A and we have got vector B. Now, this tells you that you are moving from A towards B. So the rotation is the anti-clockwise. So when you are opening a screw, when now, assuming that your hand is on top of those above those vectors A and B, and you are turning from A towards B, therefore you are turning in the anti-clockwise direction, where do you expect the screw to go? Of course, the screw is going to come out. If it was on a board like this, and you are turning it in the anti-clockwise, it's going to come out. So that direction which the screw moves is the direction which is going to be given by the resultant vector, which is the cross product of OA cross OB. OA cross OB. Okay? Now, if now we change the rotation such that now we have got OB cross OA, we have got OB cross OA, so this is the cross product, then it means if again you take your hand above those two vectors and then you rotate the screw, now you are rotating from OB towards A, so the rotation is going to be the clockwise. If you have got a screw and you are rotating it in the clockwise direction, then it means you are tightening that screw and therefore it's going to go in. Therefore, the direction in which the screw moves is shown by, or is going to denote, the resultant vector. And therefore, we conclude that in cross products, this does not assume the commutative law, which says that if you have got two vectors, if you interchange them, they are going to give the same answer. So this one, if you have got OB times, if you have got OA times OB, it's not the same as having OB times OA. So in fact, it's going to have opposite direction. So it's like now having a reverse, such that if you have got OA times OB, this is going to give you a negative of OB times OA. So if you interchange them, they give you a negative direction. So this is what we have in cross product, and this is what we are going to use even in the calculations of our problem, which is given here, which when you have A given by this vector and B given by this vector, and then you are told to get A cross B. Let's see what you are supposed to get when you have got A cross. You are going to have A cross B. So our A1, our A is going to be given, or is given by A1I plus A2J plus A3K. And our B is given by B1I plus B2J plus B3K. Then you are getting the cross product. It's A cross B. So we usually use cross to denote that. You are doing the cross not times. This is A cross B. So again, we just do like what we have done in the dot product, you multiply the whole of vector B times the first component plus the whole of vector B and the second component of J, like that. So the first case, you are going to have A1 B1 I dot I plus A1 B2 I dot J plus A1 B3 I dot K, then plus, come now to the second one, we have got A2 B1 J dot I plus A2 B2 J dot J plus A2 B3 J dot K. Now plus, now in the last one, we have got A3 B1 K dot I plus A3 B2 K dot J plus A3 B3 K dot K. Remember, you should be very keen not to interchange when you are multiplying these components. If you interchange, if here I assume that when I'm multiplying, like for instance, when I'm multiplying this and this, for instance, I have A1I times B2I, B2J, and then I interchange. Instead of having I dot J, I have J dot I, that is going to change the direction. Remember, in cross product, we have seen the direction is very important and you should not interchange because it's going to give you a wrong answer. So, when you have multiplied across each component across the other, then you are going to have that, and then just like what we said in the dot product, you are going to have I, J, and K all have got a magnitude, or have magnitude of 1, or have got a magnitude of 1, and therefore if you are doing a cross product, for instance, the first one is going to be I dot I, is going to give you I1 times 1, which is the magnitude of each of these, and then sign of the angle between them, which is 0. Sign of the angle between them, which is 0, and sign of 0 is 0. So this is going to give you 0. So all those components which have got I, all those values which have got I dot I or J dot J in them, they are going to give you an answer 0. So this is going to be the same for that which is J dot J and that one which is of K dot K. So that is going to give you an answer 0. And then on the other hand, if you take now the other one, for instance, when you have got I dot J, so this is going to have a magnitude of 1, and the I is going to have a magnitude of 1, J is going to have a magnitude of 1, then sine of the angle between them is 90, so sine 90 is 1, and therefore this is going to give you 1. It's going to give you 1. Now, here there is something, so it means all those components which have got I dot I, all this is going to be 0, this is going to be 0, this is going to be 0. So you are going to be left with those other parts. And it is very important that now when you come now to check what you are going to have in any of them, then we come back to this. We are going to come back to this vector diagram here of 3 dimension of the unit vector, and we usually take the anti-clockwise direction to be a positive direction, or to be the positive direction of movement, such that here, even in the terms of labeling, you have got I, J, K. So we have said in the explanation of the cross product that if you have got I cross J, it is going to move in the clockwise direction, and therefore the vector which you are going to have, it's going to go in the upward direction, and note that this is at right angle with both of the two vectors. And therefore, I cross j is going to give us k. K cross I is going to give us j, like that. So we go to the next vector, okay? And then if it happens to have a situation, that's why I told you it's very important that you do not interchange the vectors. If now we have got k cross j, so this is moving in the clockwise direction, and therefore this is going to be the reverse, and this is going to give us a negative. It's going to be give us I, but it's going to be negative because it's going in the negative direction. So k cross j gives us negative I cross k gives us negative j. Okay? So when we apply that knowledge here, we are going to see that when we have got the first case, so our A cross B is going to be, or is going to give us, now this is A1, B2, this is IJ, so it is moving the forward, and therefore we go to the next component, which is going to be K. Then the second one, we have got A1, B3. Now here we have got IK. So when you have got IK, for instance, just like what we have said, this is IK. It is going the opposite direction. So what we are going to have is J, but now negative. Okay? So this is going to be a negative J. Okay? It's going to change the sign there. And then we have got the third one, which is A2B1. A2B1, again, J, I, it is again going in the opposite, in the reverse direction, and therefore again here we are going to have a negative, and this is going to be K. And then we have the other one, which is A2B, A2B3, we have A2B3, JK. So JK is going in the forward direction, and therefore it's going to be positive. So this is going to be positive, and then JK is going to give us I. So give us I, and then we come to this one. We have got A3B1. You have got A3B1. I first of all write without putting the sign here, and then I get the direction from the cross multiplication of the two components. So Ki is going the forward direction, and therefore this is going to be plus, this is Ki is going to be given by J, and then lastly we have got A3 B2 Kj. Kj is going the reverse direction, and therefore is going to be negative I. That is going to be negative I. Then from there, you put the like terms together. And the like terms together, whatever that we have is that here we have got K, here we have K, here we have K. Here we have got I, here we have got I. So we start them like we have I, J, and K. So if we start with I, we are going to have, this is going to be, this is positive here, but this is negative here, such that you are going to have A2B3 minus A3B2, that is going to be I, that is going to be I, and then J we have got, we have the positive one is this one, and here this is negative one, and therefore we are going to have, this is positive, A3 B1 minus A1 B3, that is J, and then plus the last one, which is K. This is positive and this is negative, which is going to give us A1 B2 minus A2 B1, or that one is K. So that one is K. So note that in each of these components we have got the vectors, and these unit vectors are the one which tells us that the answer which you get is a vector quantity. It's a vector quantity. So this is how you get the cross product of two vectors. For instance, what you had as A cross B, the answer which you are going to have is given by that. So if you go back to our slide, which is so if we go back to our slide, we have got an exercise here which you need to tackle, and the exercise is telling you that for the vectors A1 plus 4j minus 2k and B is equals to 2i minus j plus 3k, then determine A cross B, okay, and then you get the magnitude of A cross B. You get the magnitude of that. Okay, given that, then it is very possible to do that following what we have done in this other example. Now, here we have got a summary of the differences between the dot product and the cross product. So the dot product is also called the scalar product, and the cross product, as you have seen, is also called the vector product. So the first difference is that the answer which you get in the dot product, it is a scalar. It does not have directions. It just have a magnitude. The product which you get in the cross product of vector product, it is a vector. It has got both magnitude and direction. Now the second difference is that the formula of getting the dot product is A dot B is given by magnitude of A times magnitude of B cos of the angle between them, and the formula of getting the cross product is A, which is A cross B, is going to be the magnitude of A times the magnitude of B, then sine of the angle between them, and there is a U there with, should we have a hat to note that the answer which you get here, it is going to be a vector. And then we have also said that the dot product follows the commutative law of algebra, which when you have got A dot B is going to be the same as B dot A, but when you come to the cross product, you get that A cross B is not the same as B cross A. Okay? And then lastly, we have also seen that when you have got two vectors which are perpendicular to each other, that is in the dot product, two vectors which are perpendicular to each other, the answer which you get when you have the dot product is going to be 0. Like what we had, like I dot j, which are right angles, the cosine of 90 we have seen it's 0, and therefore that's what you have as the two being perpendicular to each other, giving us an angle, a value of 0. On the other hand, at the cross product, if you have got two vectors which are parallel to each other, like what we have had, I dot I, j dot j, they are parallel to each other, and therefore the answer which you are going to give when you have the cross product is going to be 0. So this is the summary of the dot product and the cross product in terms of their differences. And we have that as the end of our first lesson, and very much thank you. So we shall meet in the second class.
These televised lectures supplement our robust online learning going on our MKU online platform. You can view more on our televised lectures via our online platform. We are in a digital era, and Mount Kenya University knows this. The following are the steps to follow so as to complete your online application. Download the application form from the website www.mku.ac.ke. Attach copies of your academic certificates and ID. Pay the application fees via M-Pesa pay bill number 270988. Your ID is the account number. 2,000 shillings is the charge for a postgraduate. You can also deposit in the bank accounts provided on the website. Then email all the above to apply@mku.ac.ke.